All right, good morning, you guys. Today we're taking on Quiz 9 review. Crazy. It's our last quiz on our content that we've been covering. All right, so first up, I'm saying find the percent of a standard normal model in this region. It may help to sketch a visual. So first up, I see that I have absolute value bars, so I know that that reads as a magnitude problem. So if I sketch out a pretty visual, here's my normal curve, here's my mean, right smack in the middle. We're saying that the distance from the mean is less than 1.4 standard deviations. So I want to go 1.4 standard deviations over to the right and to the left. So here z would be negative 1.4, and here it would be positive 1.4. So less than 1.4 from the mean, less than would be the in-between part from here to here. Okay, so now when I type this into my calculator, I can say normal CDF. I'm going to go from negative 1.4 to positive 1.4 with a mean of 0 and a standard deviation of 1. So if I type that in with you, clear that. So I'm hitting second varse, normal CDF, negative 1.4, comma, 1.4, comma, 0, comma, 1. And we get 0.8385. So approximately 0.8385. And as a percent, 83.85%. Okay. Next, find the z-scores that correspond to the middle 70% of our data. Okay, so here is my normal curve. You know I love a picture. Middle 70, so roughly from here to here, there's my middle 70. So I'm looking for the marker here and here. So I need to remember that the remaining area is 30%. So if I split that two ways, I have 15% here and 15% over here. I know that these z-scores here and here, they're going to be opposites. This will be the negative, this will be the positive. So if I find one, I will find the other. I don't have to do the calculation twice. I should know that they're going to be opposites. They have the same magnitude, the same distance from the mean. So here I'm going to use inverse norm. Okay, the area below is 0.15 with a mean of 0 and a standard deviation of 1. So let me plug that in. So second varse, inverse norm, 0.15, 0, 1. So here I'm going to get a z-score of about negative 1.0364. So right here would be the negative 1.0364, and then its positive counterpart, 1.0364. So again, they are opposites. They have the same magnitude, the same distance from the mean, right? My mean would be right smack right there. So the z-scores are going to be opposites. All right, moving up, some context. So without properly working spark plugs, a vehicle will not run. For a specific vehicle, the spark plugs are supposed to have a gap between 1.4 millimeters and 1.6 millimeters. That feels important. I'm going to underline it. Any spark plugs with gaps larger or smaller than this will fail inspection and be discarded. At the factory, the machine that sets the gap follows a normal distribution with a mean of 1.5 millimeters and a standard deviation of 0.075 millimeters. Okay, what percent of spark plugs will pass inspection? So just a reminder that it says, well, it's going to pass if the gap is between 1.4 and 1.6 millimeters. Okay, that's the statement that was right there. So if I visualize it, I'm looking at from 1.4 to 1.6. So I just want to summarize my mean and standard deviation. I usually do that off to the side somewhere. So here's my mean and standard deviation for this distribution. So my mean right here, right, there's that mean, that's the 1.5. So we're saying, okay, 1.4, 1.6. Okay, this is where it will pass from here to here. Okay, so now that we know how to use normal CDF for raw data, I can type in those constraints. So normal CDF, low to high, so 1.4 to 1.6. The mean is 1.5, and the standard deviation is 0.075. Okay, so if I type that in, here we go. So here I have normal CDF, 1.4 to 1.5. The mean is 1.5, and the standard deviation is 0.075, just like that. So I'm going to get about 0.8176. And we're talking percent, so we'd say, well, it's about 81.76%. Okay, find the 25th percentile of gap widths. So 25th percentile, I can think of that as an area or a proportion below of 0.25, right? So if I visualize it, I always love a visual. Here's that lower 25% right there, right? That bottom 25%, and we're looking for the marker right there. The mean, of course, would be right about there. All right, so here I'm going to have to use inverse norm. The area, the proportion below is 0.25. My mean is 1.5, and my standard deviation, 0.075. So if I type that in, I'm going to get 1.4494. So that is the gap width. 1.4494 millimeters. So I can use inverse norm for my raw data. If I can tell it the proportion below, the mean and standard deviation for the distribution, it will pump out the observation. If I had used 0, 1 instead, mean of 0, standard deviation of 1, it would pump out the z-score, and then I would have had to plug into that x equals mean plus z-score times standard deviation formula to get to this number right here. So we have some options for how to get there. I'm trying to show you all the shortcuts now. Let me slide it up. All right, find the IQR of spark plug gap width. So IQR, we know that that is the middle half of our data, the middle 50%. So we're looking at the Q3 minus the Q1. So Q3 minus Q1. So we want the range of the middle half of data. So here we know that this would be the area below of 0.75, and here area below of 0.25, right? Because that is the 75th percentile, the 25th percentile. So I will use inverse norm with 0.75, 1.5, 0.075. So raw data, again, it's going to pump out the observation. And this one, inverse norm, 0.25, 1.5, 0.075. And again, it's going to pump out the observation. So if I do this one with you, second verse, go down to inverse norm, 0.75, comma, 1.5, comma, 0.075. Here we get an observation of about 1.5506. Okay, and just a reminder that that is millimeters. And then over here, same idea. I'm gonna retrieve my previous answer and just type over it because I know that's going to be a 2 right there. And that gets me 1.4494. And again, millimeters. I have my raw data here. So I know that this is the observation. So all I have to do then is subtract. What is the difference between these two? So we get about 0.1012 millimeters. Okay, so again, that is the range of the middle half of our data, the middle 50% of our data. So the IQR is 0.1012 millimeters. All right, next up, if we have 1,000 spark plugs randomly selected, how many have a gap larger than 1.6? So larger than 1.6. So if I visualize this, here is the mean. Here, x equals 1.6. Okay, larger than that, so I'm looking at the upper tail, right? So I know I'm going to infinity. My placeholder is 9,999. So when I type this in, I can say normal CDF from 1.6 to infinity, but my placeholder 9,999 with a mean of 1.5 and a standard deviation of 0.075. So I'm going to come up with 0.0912. And then that would be the proportion that falls in this region. So 9.12% would fall in this region, having a gap larger than 1.6 millimeters. So since we're looking at 1,000 spark plugs, we just have to now multiply those two figures. So 0.0912 multiplied by 1,000 will get me 91.2. Okay, can't have a portion of a spark plug, so we would just round to the nearest integer value. So we'd say, well, that's about 91. Okay, and then one last variation right here. What spark plug gap width represents the top 10% of spark plugs? So top 10%, we know, okay, got to convert that. Think of it as the bottom 90. So here is my mean. Here is that, top 10% right there. But I have to think of it as what's below. So that's the bottom 90. So top 10 is really bottom 90. I always have to think about it as the below. So I know that that means that the area below would be 0.9. And then I can use inverse norm, 0.9, comma, 1.5, comma, 0.075. So again, I know, based on my distribution, I know the actual mean and standard deviation. I don't have to convert to z-scores anymore. So here I can pump out the actual x value, the observation. So it's going to give me 1.5961 millimeters. All right, so this front page, a nice review. We've been working on this unit for quite some time. I'm just showing you all of the fancy calculator tricks now. All right, please flip it over. Let's go to the back. All right, so a little recap of control charts. So use the blank control chart to illustrate a process where the standard deviation has clearly decreased. So if my standard deviation has clearly decreased, that means that I'm just seeing less variation. My data is more consistent. I'm seeing less variation. So with our control charts that we've looked at, my big takeaway really is, can you visualize a shift in mean? Can you visualize a shift in standard deviation? So here, less variation would mean that my data should be more tightly packed together. So I should have, a bulk of my data kind of clustering right here near that center line. So I'm just giving you guys kind of an example of what it could look like. So I'm just looking at data that's just more tightly packed together in that C zone. So that C zone, remember, it represents one standard deviation away from the mean. So right here, this one is the mean. This would be one standard deviation above, two above, three above, one below, two below, three below, just like that. So we know that here to here should be roughly 68% of our data. So we're seeing that things have just tightened up, right? Our standard deviation, all of our data, right, or most of it is in that C zone. The data is more consistent, less variation. If I said standard deviation has increased, I would have seen data that's more erratic, more volatile, right? More fluctuating up and down. All right, next problem. Find the missing standard deviation. So we are given the mean. We're told that 89% of our data falls below a 62, and that 62 is the observation. That's the X. We want standard deviation. So if I visualize this, here's my normal curve, here's my mean of 50, right? That's my mean. 89% below 62. So here is the X value of 62, and we're looking at 89% falls below it. Here's that 89%. Okay, so here I know that I'm going to have to use X equals the mean plus the z-score times the standard deviation. Remember, that's just derived from our z-score formula, where z equals X minus the mean over the standard deviation. So I could technically just plug into that formula and then solve for the standard deviation. That's fine too. I just like this revamped formula a little bit easier. That's my preference, but they both work. Doesn't matter to me. So what I know right now, I know my observation right here is 62. I know that my mean is 50. Okay, I don't know what the z-score is for this observation, but I know how to find it. So I'll leave myself a little room for that. And then standard deviation is what I'm trying to solve for. So I need that z-score, right? That's what I want. So if I look right here, I know I can use inverse norm. Proportion below is 0.89. Mean is 0. Standard deviation is 1 when I want the z-score. So when I type in inverse norm, I'm going to get a z-score of about 1.2265. So this observation, right, is 1.2265 standard deviations above the mean. So that's what's going in right here, 1.2265. So now it's just an algebra problem. I want to get that standard deviation by itself. So I would take away the 50 from each side. So 12 is equal to 1.2265 times the standard deviation. And then I want to divide away that 1.2265 from both sides. Okay, so my standard deviation would be about 9.7839. Okay, next up. So here, a large nationwide chain store requires a simple membership plan for its customers. The marketing manager believes that a new tiered membership will attract more customers and increase profits. A random sample of 341 customers is selected, and 68% of those surveyed said that they would purchase a tiered membership. Okay, so let's unpack what it's giving us. It's giving us a sample size right here. So I know that my N value is 341. Okay, this figure right here, that's 68% of those surveyed, that is a statistic. So P hat equals 0.68, and then its complement, Q hat, would be 0.32. Okay, so first thing I have to do now, is read what is my confidence level that we're setting. We want to calculate a 90% confidence interval for the proportion of customers who would purchase a tiered membership. Okay, so I have to find the critical value for 90% confidence first. Okay, so I know that that means middle 90%. Let me draw that out. Here is roughly the middle 90% of my data. I need to figure out what would be these two z-scores, right? Because when I take absolute value of it, that is going to be my critical value. So when I look at the middle 90%, I have 10% in these two tails. If I split it evenly, I have 5% here and I have 5% here. So I know that these would be opposites. They have the same magnitude distance from the mean. I just have to solve for one. And when I express it as a critical value, I only express it as a distance, as a magnitude, as this multiplier that we're going to see in our formula in just one moment. So here I need to do inverse norm. Area here would be 0.05. Mean of 0, standard deviation of 1. That's going to pump out my z-score. So my z-score would be negative 1.64. Okay, for critical values, I've always had you take the z-score to 2 decimal spots. So here I have my critical value then would be 1.64. Okay, that's my starting point. Okay, now I need to build my confidence interval using that critical value. So my confidence interval is our statistic with the margin of error attached. So statistic plus or minus the margin of error. But if I'm more technical in my formula, I would write it out like this. So my statistic plus or minus my critical value times my standard error. P hat, Q hat over N, and then square root. So statistic plus or minus my critical value, I know that right here, times the standard error. Right? We have a different word for it. We don't call it standard deviation because we don't know the true parameter. So we give it a different name, standard error. Okay, so if I plug in, my statistic was the 0.68, and then plus or minus, here, my critical value, 1.64, multiplied by the standard error, square root, 0.68 times 0.32 over 341. All right, so if I type all that in, I'm going to end up with 0.68 plus or minus 0.0414. Okay, so this is my statistic. This is my margin of error, right? We can write it as decimals. We can write it as a percent. We could actually compute it and find the window. So the three ways I'll take it as 0.68 plus or minus 0.0414. That's fine. I could say 68% plus or minus 4.14%. That's fine. Or if I actually take the 68 and add and subtract this, I could build my window as 68.8, no, I wrote that wrong, 63.86, let me just fix that, 63.86% to 72.14%. All of those would be fine with me. All right, next question that builds off of it. The company wants a smaller margin of error, right? They want to change the margin of error. They don't like up here that it's at 4.14%. So they want to figure out, well, how large of a random sample do they need to get a margin of error that is at most, that language is crucial, at most 0.02 in a 90% confidence interval. So it's saying if it's at most 2%, at most 0.02, right, my margin of error must be less than or equal to 0.02. So I'm just keeping that in mind as I build my inequality statement. So my margin of error here, I'm looking at what I calculated over here for a moment. All that's going to be different is my n value. So my n value, that's what I'm going to solve for. I want to solve for my sample size that would create a margin of error that is less than or equal to 0.02, right? At most 0.02. So I'm going to take, right here, I'm going to take that margin of error. So 1.64 times the square root of 0.68 times 0.32 divided by n. And I want it to be less than or equal to 0.02. So that's my starting point. Now I'm going to have to use some algebra to get the n value all by itself. So I'm going to use my fancy different colors just to help you see all the steps involved here. So I'm not going to touch my calculator until the very end. I don't want to build off of a series of rounded answers. I want to type in at the very end. So first things first, I'm going to divide each side by 1.64. So right here, that will go 1 to 1. So now I have the square root of 0.68 times 0.32 over n is less than or equal to 0.02 over 1.64. Okay, now, again, I'm keeping my eye on the prize. I want to get to the end. I can unlock the square root by squaring both sides. So I'm going to raise each side to the second power, and that's going to unlock my square root. So I now have 0.68 times 0.32 over n less than or equal to 0.02 over 1.64 squared. Okay, so now I want to get the n, right? I want to get the n out of the denominator position. So I'm going to clear my fraction by multiplying each side by n. So on the left-hand side, that will clear it. So now I have 0.68 times 0.32 is less than or equal to 0.02 over 1.64 squared times n. So what I need to do last, I need to get the n all by itself, is divide each side by 0.02 over 1.64. To miss anything. Okay, so there we go. Let me just make sure you saw. I know you heard me, but I want to make sure that you can understand the steps. Okay, so here what I had in that previous step, right, I divided both sides by 0.02 over 1.64 squared, right, and that will cancel away. So now I have that n is greater than or equal to this entire chunk right here. So I know that the screen froze for a moment, but I think we're good now. And now let me show you how you could type that in. So again, I just want to make sure I preserve my order of operations. So my numerator is 0.68 times 0.32. I'm putting that in parentheses. I'm going to divide by, and I'm going to open two sets of parentheses here. So two sets like that, because I want to have 0.02 divided by 1.64 inside parentheses. I want it to be squared like that, and then I want to close that second set of parentheses. So I'm doing that just to make sure that I am preserving my order of operations. I am essentially giving parentheses here and here. So let me just make sure you can see that one more time. Let me go back. So my numerator in parentheses, right? I see the product of 0.68 and 0.32. And then I'm dividing by the package that's on the bottom, right? So this is what it looks like for what I have it typed in as. Okay, so again, it's like I have this extra layer of parentheses right there. So I hit enter, and this is the number that comes out. So I get that n is greater than or equal to 1,463.1424. Okay, so I know that n has to be an integer value, so I'm looking for the nearest integer value that makes this statement true. So let me write that. Round to the nearest integer that makes the statement true. So to make it true, let's think for a second. Let's say that I made it 1,463. Would that 1,463 be more or equal to this figure right here? No. It has to be the number that is moving up. So I know that when I round to the nearest integer, I'm always going up here to the next one to make this statement true, where n has to be greater than or equal to that integer value. So the integer value would have to be then 1,464. So my sample size would be 1,464. Okay, this would give me a margin of error that is at the very most 2%, 0.02. All right, one last problem. Problem 7. All right, at fast food restaurants, the lids for drink cups are made with a small amount of flexibility, so they can be stretched across the mouth of the cup and then snugly secured. When lids are too small or too large, customers can get frustrated, especially if they end up spilling their drinks. At one restaurant, large drink cups require lids with a maximum diameter of 4.05 inches. The restaurant's lid supplier claims that the diameter of the large lids follows a normal distribution with a mean of 3.9 inches, or 3.98 inches, let me underline that, and a standard deviation of 0.02 inches. The supplier is considering two changes to reduce the percent of its large cup lids that are too large to 1%. One way is to adjust the mean diameter of its lids. If the standard deviation remains at 0.02 inches, at what value should the supplier set the mean diameter so that only 1% are too large to fit? Okay, so let's just think about what we're asked. We're told that it's normal. We are trying to find this mean value with a standard deviation of 0.02, right? That's what we're told right there. We're keeping that standard deviation fixed. Okay, if I visualize my situation, here's my normal curve, right? We want it to be limited to the lids that are too large, should be only 1%. So here's that 1% right here. Which means that, well, 99% are fine. Okay, so there's that bottom 99%. So right here, what does that correspond to? So here we're saying the maximum should be 4.05. So that number is really crucial. That goes right here. And inches. Okay, and then just to remind you, the mean, that is what we are trying to capture, right? We're trying to get to that number. So if I want to figure out my z-score, because again, I don't have these two numbers. That's what I'm trying to find is my mean. I have to figure out my z-score first. I need to end up using the x equals mean plus z-score times standard deviation formula. And right now, I know that x is 4.05. I don't know the mean, so I'm going to leave some room for it. I know that I'm going to add it to the z-score that I can find, and a standard deviation of 0.02. Okay, so I know mean, right? That's what I'm going to solve for. So big gap, there's my mean, and this I'm going to solve for in just a moment, my z-score. So here, I need to use inverse norm. Okay, my area below would be 0.99. Mean of 0, standard deviation of 1. That's going to pump out a z-score of 2.3263, which goes right here. Okay, and then again, I'm just back to essentially an algebra problem, right? I got to get the mean all by itself. So I'm going to have 4.05 is equal to the mean plus. Okay, when I crunch this product, I get 0.0465, and then I want to take that away from each side. So 0.0465, 0.0465. Okay, so my mean ends up being about 4.0035. And my units are inches. All right, there we go. That's the last example I have for today. Please make sure that you look through all of your notes, look through all of your older topics, look at that review sheet, come into office hours, ask me good questions. I hope you guys are doing well. Have a good rest of your day.